Hi, good morning. Thank you very much. Thanks to the organizers for the invitation. I'm going to give a course on the local dynamics of tangent to the identity biholomorphisms in dimension 2. So, except for today, where I will speak a little bit about the dynamics of germs of vector field in C2, my object of interest will be a map F, which is a germ of biholomorphism which has 0 as fixed point and is tangent to the identity. Okay, so the linear part is the identity, C plus higher order terms, and we will be interested in the question of studying the orbits of this map. And more precisely, the existence of invariant manifolds for F. Okay, so as we will see tomorrow, there is a vector field which is deeply related with F. Which is so today I will review some results about vector fields in dimension 2, which are probably very well known to most of you. So I will speak about the existence of the lecture about today. Okay, so you can associate to F a vector field. It will be formal, but today I'll be only talking about analytic vector fields. So in the lecture today, I will consider the problem of invariant curves for vector fields in C20. Okay, so I will be dealing with a vector field X, a vector field in C2, 0, which is singular at the origin. It's not necessarily an isolated singularity. I will not be talking about foliations because my object of interest is the map F. So really, I'm working with the vector field, not with the foliation associated to it. And so we have that in coordinates. We can write Ax as A of xy, partial with respect to x, plus B of xy, partial with respect to y. Okay, they are analytic. Tomorrow we'll talk about formal vector fields, but for today's lecture, my vector field is analytic. Okay, so, well, just a few definitions before defining what an invariant curve is. When A and B have no common factor, so 0 is the only is an isolated singularity, and A and B have no common factor, we say that X is saturated. Okay, and we can always write X as H times X bar, where X bar is saturated, and we call it the saturation of X. Okay, so as I said, I will only be interested in the problem of existence of invariant curves. So let me just remind what an invariant curve is. So consider an invariant curve which is given by an analytic curve, which is given by the zeros of an analytic function. Okay, we say that it is invariant when x of g, we say that it is invariant if x of g is a multiple of g. Or equivalently, we consider a parametrization of the invariant curve. Gamma t is a parametrization of gamma. We have that x in gamma of t is a multiple of gamma prime, which means with these coordinates I wrote, it means that A of gamma of t, gamma 2 prime of t, is equal to B of gamma of t, gamma 1 prime of t. Okay, so this is the object we are looking for. I will talk both about analytic invariant curves and formal invariant curves, okay? So for formal ones, they don't have a geometrical meaning, but this equation of being invariant can be defined essentially the same way. So this function g can be either analytic or formal, and this parameterization, the same thing. Okay, so gamma will be both either analytic or formal. Okay, so the first result I'm going to review for most of you is Seidenberg's resolution of singularities. Okay, so we have a singularity at 0 that in principle can be very complicated, and Seidenberg's resolution of singularities tells us that we can perform a finite number of blow-ups, and with this transformation we find only singularities that are of an easier type, what are called simple singularities. Okay, so before that, let me review. I guess most of you know that also, but let me review what we get when we blow up a vector field. Okay, so we blow up. We consider a blow up centered at the origin. We consider pi, blow up of C2, centered at the origin. We can write x in coordinates, this expansion as homogeneous polynomials of a and b. Ak plus ak plus 1. Bk plus 1, where these are homogeneous polynomials, aj and bj are homogeneous. Sorry, yes, thanks. Are homogeneous polynomials of degree j, and ak bk is non-identical 0. Okay, this is k is the order of the vector field. Okay, so if we consider in the first chart of the blow up, where the map is given by pi of xb equals xb, we can compute the blow up of the vector field. Pi star of x is equal to x minus 1 times x ak of 1b plus x partial with respect to x plus, here we have bk of 1b minus b ak of 1b plus okay, so this is the vector field in the first chart of this blow up. So we have two possibilities here. We have one possibility where this is identically 0. We have that polynomial ak of 1b, sorry, bk of 1b minus b ak of 1b is identically 0, so we can take x as common factor in that expression in the right hand side. X is a multiple of that, Okay. So in that case, we say that pi is dicritical. So in that case, ak of 1v cannot be 0, so x equals 0 does not divide the saturation of x. X equals 0, does not divide, x does not divide the saturation of pi star of x. Okay, so in the points we have here something which is invariant for x. The exceptional divisor is invariant for x, but not for its saturation. And we have that in the points where ak of 1v is non-zero, we have the saturation is regular, so we find invariant curves. In the points where ak of 1v is non-zero, okay, the saturation is a regular vector field, so we find invariant curves which are transverse to this to the exceptional divisor. There are 2 pi minus 1 of z. Okay, and in the other case, we have bk of 1v minus v ak of 1v is not identically 0. We say in this case that pi is non-dicritical. So x equals 0 is invariant for the saturation, and the singularities on the exceptional divisor are given by the zeros of this polynomial. The singularities for the saturation of pi star of x on the exceptional divisor are given by the zeros of this bk of 1v minus v ak of 1v. Okay. So these points that are singular for the saturation, we will call them strictly singular points. So these points, the singularities of the saturation of the vector field, will be called strictly singular points. Okay, we can do the same computation in the other chart. We get an analogous computation. So what we have is that in the non-dicritical case, the strict singularities, the strictly singular points, are given by the zeros the strictly singular points are given by the zeros. Are given, sorry, by the lines that correspond to the zeros of the here, sorry. Are given by, are the lines, are the points that correspond to the solutions, zeros of what is called the tangent cone, which is this homogeneous polynomial px of xy, which is x bk of xy minus y ak of xy. Okay, we have that homogeneous polynomials. Its lines after blow up will correspond to some points on the exceptional divisor. And in the non-critical case, these are exactly the points where my vector field is strictly singular. Okay, so let me define what a simple singularity is. So we say that a vector field has a, I will define first what an elementary singularity is. We say that X has an elementary singularity at 0 if its linear part, with the same notation as before, its linear part is non-nilpotent. So we have two eigenvalues, and at least one of them is non-zero. Has eigenvalues lambda mu with lambda different from 0. Okay? And we will say that it has a simple singularity. I will not use, since I will be relating these results tomorrow with some results about diffeomorphisms, I will not use the standard definition of a simple singularity. I will change it a little bit. So we say that if, moreover, we have that the quotient of the eigenvalues is not an integer, a natural number, or the inverse of a natural number, we say that it is simple. Okay? If, moreover, mu over lambda is not in n or 1 over n, okay, it can be 0, we say that the singularity is simple. We say that the singularity is simple. Okay, so we have two possibilities here. Either the quotient is 0, mu is 0, or mu is different from 0. When mu is different from 0, we say that the singularity, the simple singularity, is non-degenerate. And when mu equals 0, we say that the singularity is a saddle node. Okay? So a remark, as I said, usually in the definition of simple singularity, one imposes a little more about the quotient of the eigenvalue. We impose that the quotient is not a positive rational number. Remark in the classical definition of simple. Usually, simple means that the quotient of the eigenvalue, mu over lambda, is not a positive rational number. Okay, so so Seidenberg's resolution of singularities tells us that after a sequence of blow-ups, a finite number okay, so we have the singularity, we blow up, we obtain some strictly singular points. If they are not simple, we continue blowing up. Okay, so in a finite number of steps, we have that all the strict singularities will be simple. Or, yes, all the simple singularities we have here will be simple. Okay. There exists a finite sigma, a finite composition of blow-ups centered at these strictly singular points, strictly singular points, such that, in the final case, such that for all p in the exceptional divisor, we find coordinates with xy, such that we can write the transform vector field at P as an equation of the exceptional divisor, which is given either by, it has one component or two components, so it will be x to the m, y to the n. And here we have this, let's say x tilde, which is either non-singular, or if it's singular, it has a simple singularity. Either non-singular or has a simple singularity. Okay. So how does that helps us to find invariant curves? We have that if we blow up the vector field, we have an invariant curve, and we, okay, let me write it. We have that gamma is invariant for x if and only if this condition is preserved by blow-up. And only if the strict transform, it's a strict transform, is invariant by pi, by a blow-up, is invariant for pi star of x at the point corresponding to where q is strict transform gamma tilde, the intersection with pi minus 1 epsilon. Okay. So this condition of being invariant is preserved by blow-ups. So, so if we manage, well, if we don't lose any invariant curve doing blow-ups, and if we find one invariant curve at the final resolution, we can blow it down to an invariant curve for the vector field x. Okay, so now let's analyze what happens in the simple singularities. So now we'll see what happens in the existence of invariant curves at simple singularities. Okay, so we have a theorem by Briot and Bouquet. Which tells us that if we have a simple singularity, we find two invariant curves for x. If x has a simple singularity, then there are two invariant curves for x that are non-singular and transverse each other, that are non-singular and transverse. And whose tangent direction is an eigenvalue of the linear part. And tangent to the eigendirection of the linear part of x. And if, moreover, the corresponding eigenvalue is non-zero, this in principle formal, sorry, I should say explicitly what we have. In principle, they are formal, but if, moreover, the eigenvalue corresponding to this direction, tangent direction, is non-zero, we can guarantee that the invariant curve is analytic. If, moreover, the corresponding eigenvalue is non-zero, if the corresponding eigenvalue is non-zero, that formal invariant curve corresponding to that direction is analytic. Okay, so let me give an idea of the proof of this result. It's not complicated. Okay, I'm not saying anything about uniqueness. Okay, or uniqueness can be guaranteed only with the usual definition of the quotient of the eigenvalues being non-rational. In here, in principle, we could have more singular formal invariant curves. Okay, so they are not unique. Okay, so the idea of the proof, well, more or less the steps of the proof. Okay, so we have a simple singularity. The quotient of the eigenvalues is not a natural number of the inverse of a natural number. So we can write x as lambda x plus higher order terms, mu y plus higher order terms partial with respect to y. Okay, we first perform a blow up. Assume that we are in the first chart of the blow up. Okay, so we have that when we blow up this a simple vector field, a vector field with a simple singularity, we obtain a non-decritical blow up, and the transform at the origin here, pi star of x is given by x times lambda plus higher order terms plus mu minus lambda y plus higher order terms partial with respect to y. Okay, so we have that the exceptional divisor is an invariant curve, and we look for another invariant curve using indeterminate coefficients. Okay, we look for, sorry, I call it V. So we look for a formal invariant curve of the form V equals the sum of an x to the n. Okay, we do the computation equating the coefficients of x to the n, and we get an equation of the form n plus 1 lambda minus mu times an. Okay, we are a equal sum polynomial which depends on these coefficients and the previous coefficients of a. Okay. So we get something here which is a polynomial, depending of course on the coefficients of the vector field and also on the first terms, a1, an minus 1. Okay, so if this is invertible, we can find a formal solution, and this is invertible because my assumption is that the quotient of the eigenvalues is not in n or in 1 over n. Okay, this can be inverted, and we find a formal solution. Okay. Yes, for the other chart, yes. I will explain it a little quickly, but I will do it, yes. This is different from 0 by hypothesis because my singularity is simple. So it can be inverted, and we find a formal invariant curve. Okay, how do we prove convergence? I will only give the idea. So here, if we have that lambda is different from 0, if lambda is different from 0, this curve, which in principle is only formal, can be shown to be convergent. The formal curve, invariant curve is convergent. Okay, so I will not do the proof, but the proof is not complicated. It's just an argument of a majorant series. We construct a solution of an analytic solution of an analytic equation, which whose coefficients bound the coefficients we have here. Okay, so with majorant series, we can prove the convergence of this formal curve in case the corresponding eigenvalue is non-zero. Okay, in the other chart, we can do the same thing. Pi of ty, we have the same thing. Here the map will be, the transform vector field will be lambda minus mu times x plus higher order terms plus y mu plus something partial with respect to x, partial with t, partial with respect to y. We do the same computation. Now we have that y equals 0. In this chart, y equals 0. Since it's not critical, this is invariant. And we look for t as bn y to the n when n is greater or equal than 1. We do the same computation, and we find something which is lambda minus n plus 1. I think it's mu bn. It's a polynomial, depending again on these coefficients and the previous ones. Bn minus 1. Okay. So by hypothesis, this is non-zero. We have a formal curve, which is, in the case mu different from 0, which converges in case mu is different from 0. Okay, and as I said, they are not necessarily unique. They are only unique with the classical. We can only guarantee uniqueness with the classical definition of of simple singularities, imposing, moreover, that the quotient of the eigenvalues is not a positive real number. Okay. So here they are. We found them unique as non-singular invariant curves. Well, let me just say it. If we moreover impose moreover that the quotient of the eigenvalues mu over lambda is not a positive rational number, they are the only invariant curves. This, we find this here. Of course, they blow down to these invariant curves. We find here one gamma 1, gamma 2, and we blow them down, and we find these two invariant curves. Okay, they are the only invariant curves for X. Okay. So, since I think I will use the name in the next sessions, when the corresponding eigenvalue is non-zero, we will say that the invariant curve is strong. Okay, in this case, we say that the formal curve is strong. In fact, it's analytic, the invariant curve. We call it strong invariant curve. And in the other case, if it is zero, we call it weak. So this, when we have a simple singularity, we have two invariant curves, and at least one of them is strong, it's convergent. Okay, the other one can be divergent, as the classical example of Euler's vector field shows. Yes? Sorry? You refer to the definition of the classical? Yes, sorry, the classical, it's for the people who are familiar with this one, because I'm presenting this because I want to relate it with some results about diffeomorphisms. So usually, in the classical definition of simple singularities, when you apply Seidenberg's resolution of singularities, you impose this one, this condition. You don't need that condition to show the existence of these invariant curves, but you need it to show the uniqueness. Okay, so if you moreover work with the classical definition, you have that they are the only invariant curves. If you do not impose that, you have these two invariant curves, and you can have more singular invariant curves. Okay, so it's not important for what I will do. I'm working with that definition of simple because it's the one that will be related to the results I will present tomorrow. Okay, but the difference is that one. It's just the question of uniqueness. Okay. Who is asking? Sorry. Yes. I'm not really sure of the name. It's simple reduced. I've seen a lot of names. I'm not really sure. They are better. Yes, of course, they're simpler. Yes. Yes, they are simpler. You can guarantee you have this linear part. You can arrive at them at the final situation, and of course you can make a study at least of the invariant curves. Yes, of course. This is one of the main reasons. It's not the only one. They are easier to analyze if you want to make the study of the behavior of the vector field around the singularity. Okay, but even for this part I'm presenting, this is something you can do when you have a linear part. If you have this vector field. General vector field, it's more difficult to provide the existence of invariant curves. Okay, so yes, they are simpler. Yes.
Thank you. Should we think of simple as close as possible to non-singular that we could possibly hope?
Yes. I don't know if it's non-singular, but the simplest singularity maybe you can think of.
Is the better you can hope making for what?
Yes. Yes. when you blow up one which is element simple, well, with my definition, you do not get simple ones, but you get almost simple ones. You get two elementary, and one of them is simple. And with the classical definition, would you blow up and you continue staying with the simple singularities? Okay, so it's the easiest you can get. Yes.
And there is a classification in small dimensions and there is no classification in large dimensions. So with here we have something like that. We have something singular. We can classify in simple cases. We don't have maybe just to classify singularities in when rank population is more than one, for example, and things like that. But I mean, it's not like non-singular.
No, yes, no, they're non-singular. No, yeah.
We do have classification, but it's our luck that in small cases Is it reasonable or not? I don't know. I'm not an expert.
I'm not sure I understood very well, but I think so. Yes.
But yes, I think that Callum is going to speak after all, from the point of view of minimal model programs. So
They are called canonical and terminal singularities.
Yes.
In the language of
yes. Okay.
But let's,
okay.
Let's continue.
Okay, so as I was saying, these strong invariant curves are always analytic, and the weak invariant curves may be really divergent. So, as a remark, as an example, weak formal invariant curves, weak formal invariant curves can be really formal, can be divergent, can be really divergent. Okay, so if we do not impose this condition about the having a non-zero eigenvalue in the tangent direction, we can have a divergent, a really divergent formal curve, as shows the example of Euler's vector field. Okay, so here we have this x equals 0, which is the strong invariant curve, and if we do the computation here with the indeterminate coefficients, we find that this is n factorial x to the n plus 1, if I'm not mistaken. So we have something which is really divergent. Okay, so I will not go into details in this part, but let me just mention, because in the next lecture, in the two next lectures, I will talk about the problem of realization of formal invariant objects. Okay, so let me mention that here, even though the weak invariant curves are divergent, they are summable. Okay, so summability is a Borel-Laplace summable. It means that we can perform a transformation which allows us to obtain sectorial realizations of them which are still invariant. Okay, they are always summable. Okay, I will not go into the details, but the thing is that with this transformation, this Borel-Laplace transform, we can like sum them in a wide sector. In fact, there exists a map. There exists a sectorial realization of them, okay, having this expansion as asymptotic expansion of Gebre type, and which are also invariant, There exist sectorial realizations of them, which are invariant. Okay, so we can also find, although they are divergent, we can find sectors of realization, and we find invariant objects also. Okay, so what happens when the singularity is elementary, but it's not simple? Also, I will relate it tomorrow to one of these, the results I'll present tomorrow. So what happens when we have an elementary singularity, the quotient, we have a non-zero eigenvalue, but the quotient is either natural or the inverse of a natural number. If the singularity is simple, is elementary, sorry. So one non-zero eigenvalue, but not simple. Okay, so assume, for instance, that mu is a multiple of lambda. Okay, so we can do this exact computation in one of the cases. Let me see if mu is over lambda is not natural, is natural number. We cannot do this thing, this computation. Okay, here we have a problem because mu over lambda can be a natural number, so this computation does not work, but this works. Okay, so we find one convergent invariant curve, the same proof. Okay, we can also blow up and do and apply that result. We find a strong invariant curve but here, in principle, we can have a problem depending on the polynomial we have here, and maybe we do not have even a formal invariant curve. Okay, with but in the other direction, the direction of the other eigenvalue, let's say in the other direction, we might not have formal invariant curves. Okay, but we also have, again, this will appear also in the lecture of tomorrow, we have a more generalized invariant object. Okay, so we have Poincaré-Dulac normal form, which tells us that in this case, when we have a simple singularity, an elementary singularity that is not simple with this condition, then we find X is analytically conjugate to this vector field. This is lambda X plus mu, it's k lambda y plus a x to the n. We have here, x to the k, the resonant terms, okay, partial with respect to y, where a is a complex number. Okay, so what happens? We have two possibilities here. Either a is equal to 0, and we find invariant curves, an infinite number of invariant curves. It corresponds to the critical blow up at some point in the desingularization, but otherwise, okay, so if a is different from 0, if a is different from 0, we find, let me check the equation, we find we don't have a formal invariant curve in that direction. We don't have a formal invariant curve different from x equals 0. But we find something which is invariant, but we find like a particular type of transeries, a generalized series of the form, well, this is, let's see, x to the k plus a over lambda x to the k log of x for any complex. Okay, so we find an invariant object, let's say, a generalized curve of this form. Okay, so going back to the original coordinates, we find an invariant generalized curve. Okay, we find something of the form y equals ij x to the y x to the n k, sorry, log of x to the j, which is invariant, okay, and analytic. So again, we don't have exactly the same definition we were considering. We only have this converges in a sector, and we find again we find that this invariant object, generalized curve, let's say, is invariant. Okay, so just to finish, let me just say how these two results, the behavior of a map in at a simple singularity, the existence of invariant curves at a simple singularity, and the resolution of singularities of Seidenberg help us find invariant curves for a general singular vector field in situ. So the last result I will present is Camacho-Sad result. Okay. So the theorem of Camacho and Sad tells us that in the resolution of singularities, we can always find a point satisfying the following condition. It is not a corner, and it's a simple singularity. Okay, we are in the final case after resolution of singularities, and the eigendirection, which is transverse to the exceptional divisor, is strong. Okay, so here we have it corresponds to a non-zero eigenvalue. Okay, so we can find a strong formal invariant curve. A strong invariant curve. Okay, so the theorem tells us that there exists a resolution sigma of x, and a composition as always, and the resolution I'm blowing up only strictly singular points. Okay, so there exists a resolution of x and a point P in the exceptional divisor, such that in coordinates centered at P, we have that x is given by, it's only in a component of the exceptional divisor, x to the m, x equals 0. And here we have that we can write lambda x plus higher order terms okay, so we have that it's It's not a corner, okay? It belongs to only one component of the exceptional divisor. It's a simple singularity, and, okay, sorry, this is sigma star of x at p. And lambda is different from 0. Okay, so the theorem we just showed is that in that direction, we find the direction which is transverse to the exceptional divisor is strong. Since this is a simple singularity, we find here an invariant curve that blows down to an invariant curve here. Okay, so we find a strong invariant curve that blows down to an invariant curve for x. Okay, I think I don't have much time to give. Okay, I will just say the. Ah, yes, thanks, thanks. Okay, so, well, I will just give the idea of the proof, of one of the proofs, a simple one given by Cano. Okay, so the idea of the original proof of Camacho-Sad, well, that you have an index of the, you introduce an index of the vector field, and you control how it behaves under blow-ups and how it behaves in a simple singularity, okay? And a combinatorial argument shows that there is a point satisfying a particular condition about the index which gives us exactly this form, okay? And there is a shorter proof which allows you to at every point of the exceptional divisor to choose a point with some property that when you arrive to the final situation, to a simple singularity, this guarantees that you are in this case. Okay. It was not very clear, sorry, but I don't have much time to go into the details. So that's the result of Camacho-Sad, the existence of invariant curves. Okay, so I'll stop here. Thank you very much.
So, are there questions, remarks? And I will just ask, since we are recording, that I will pass you the microphone if you have questions or remarks.
Yes.
No.
Sorry?
What happens when lambda equals mu?
When lambda equals mu, it's like this case. Okay, with k equals 0, k equals 1, so you have two possibilities. When you have this is 0, you blow up and you get a critical blow up, or you have here, if this is A is different from 0, you have a Jordan block, so after blow up you get only one invariant curve, you get a saddle node.
So when you make these two charts to build the invariant curves, when lambda equals mu, it should work because there is no division by 0.
So can you have lambda equal mu in a resolution of sigma?
Lambda equals mu in a resolution? No.
That does not happen.
No, it does not happen. I'm not sure I understood. No, but we are in the simple singularities. I'm assuming that the quotient cannot be 1, so they are different. Okay, so here I'm not sure if you were talking about the proof of Briot-Bouquet theorem. Maybe I was not very clear, but here you can see it. You can have A equals 1 with A different from 0, and here you see that the proof that doesn't work. Okay, in this example. Okay, you can do it like that. And it doesn't work because it's not the same expression as I wrote. When you blow up, you don't have two singularities. Okay, when you blow up that vector field, you only get one singularity. Okay, so one of the I'm writing the linear part in the two charts of the transform of the blow up. okay? Because in that case, when you have a simple singularity, you get two singularities, but in that case, you only get one. So that's why it doesn't work, the proof I did. Okay? It works only one chart.
Just a second, there's one more question.
It would be helpful to give a proof, but maybe give the idea of the proof of Seidenberg's result, but maybe not for today.
Yes. No, I mean, I never planned, I was planning to give maybe the more details about Camacho-Sad proof, but Seidenberg's, I think, I mean, you have to control some invariants, the Milnor number, but I don't think I can give.
What's the relation with resolution of singularities? That's, but maybe no.
Like the resolution of singularities of curves. Seidenberg is essentially as difficult as resolve the singularities of a curve.
Of course.
Slightly more difficult.
I think.
Considerably less difficult than resolving singularities of a circle. So it's in between a curve and a circle.
I think Lorena would. My question is not for today, but to relate with resolution of singularities, and I think it's Seidenberg's proof, or Felipe Canus, in dimension 3.
Yeah, of course, it's not as difficult as that. I'm not sure what you're asking.
My
Sorry.
question is, here there are many people used to resolution of singularities.
Mm-hmm.
So it will be helpful if you could relate your results, it's not your results, but Seidenberg's, Felipe Canus, and so on, with resolution of singularities. But it's not a question for today.
Okay. Okay.
Maybe that's also for the organizer. We asked Lorena to talk about something in a different direction. But
Yes.
she can talk in the coffee break.
Yes, I'm going in a completely different direction. I mean, it's the only thing I will be talking about the resolution of singularities in this course, but maybe for another time.
So let's thank Lorena again for the.
Thank you very much.